All right, so let's get going. Last class we started talking, actually continued to talk about reactions of alkenes. We built our little cheat sheet here, and we're just going to keep on going today and add to this. We're not going to add to it directly. We're going to do a little bit of background first, so let's do this on a new page. We're going to introduce 3 different hydration reactions. All right, and by hydration, what comes to mind immediately when I'm thinking of hydration? Water. So these are going to be the addition of H2O to an alkene. All right, we're again talking about our addition reactions. Actually, let's just use our very simplest alkene, ethene. All right, and we're going to be adding a water molecule. I'm going to draw HOH to try to give you a hint as to how you're going to add this molecule to your carbon-carbon double bond. But given what we've discussed about addition reactions, everybody take a second and predict what our product will be in a hydration of alkene reaction. Okay, so we're going to do our addition to our alkenes. So we're going to break our carbon-carbon pi bond here. So we just have a carbon-carbon single bond over here on this side. We've got 2 new bonds to those carbon atoms. What am I going to put on one side? And what am I going to put on the other side? The OH. So what was the functional group that we just made here in this hydration reaction? An alcohol. All right, so these are how we can convert our alkenes into alcohols using these hydration reactions. All right, and remember with hydrogenation reactions, we took a look at our energy diagram here, and we can do the same thing for these hydration reactions. All right, the difference being is we're starting up here with an alkene. But now our final product is an alcohol. And according to our diagram here, is this reaction favorable from a thermodynamic standpoint? Are my products lower energy than my reactants? Yes, so we would say that this is a reaction that is favorable from a thermodynamic standpoint. Again, my products being less energy than my reactants, that's good from a thermodynamics. Remember, thermodynamics, we're only paying attention to the beginning and the end. We don't care about the middle. All right, so this is an example here of a reaction with a negative delta H, or is thermodynamically favorable. All right, but just like our hydrogenation reactions, it has this very large activation energy here. And what does that mean if it has a large activation energy? So the middle of our graph here corresponds to kinetics, how fast the reaction occurs. And if it has a large barrier, does that mean it occurs fast or slow? Slow. So this is another example of a reaction that, although it's thermodynamically favorable, it is kinetically unfavorable. Which means that in order for this reaction to occur, what are we going to have to use? A catalyst. All right, awesome. And we're actually going to learn about 3 different catalysts that we can use here. But we have to use a catalyst in order for a hydration reaction to occur. Okay? So we're going to kind of break these up into these 3 different classes here. The first one, all hydration reactions. All right, but again, using different catalysts. The first one is kind of our simplest, what's called an acid-catalyzed hydration reaction. So what do you think we're going to use to catalyze? An acid, all right? And in fact, it's important for this reaction that you actually use a dilute acid. We don't want to add just pure concentrated sulfuric acid in there. We're going to use a dilute acid solution. You'll see this represented, these dilute acids represented in one of 2 ways. One is they just simply put down hydronium. Right? Remember, when you add an acid to water, you form hydronium ions. So they turn out to be the active sort of species in that reaction mixture. Or you'll see it with that specific acid listed, like sulfuric acid and water. Both of these 2 are ways of representing the same thing, are ways of representing a dilute acid. All right, so either one of these will appear in your list of reagents. In your reaction, you look in the textbook, you could see either one of these and they mean the same thing, a dilute acid. All right, so I believe in us. Usually we start out with these with these chemical equations, and then we look at our reaction mechanism. We're so good at this point that I think we can jump right in to our reaction mechanism and use that to teach us a little bit about this reaction. All right, so I'm going to start off with an alkene. I'm going to use my hydronium, my dilute acid here. And I want everybody to take a second and to identify what the nucleophile is in this mixture, and then identify what the electrophile is in this mixture. All right, what's my nucleophile? That alkene. And specifically, my nucleophilic site would be which part of this molecule? That carbon-carbon pi bond. And so what's my electrophile? The hydronium. How can we spy that this is an electrophile pretty easily? The charge, right? It's not an electron-rich species, it's an electron-poor species. But what is the electrophilic site on this molecule? So the O can't accept any more electrons. It's got a full octet. So this is an example of our electrophile where we have a good leaving group. That's what role this thing's going to play here. My electrophilic site in an acid is always that proton, right? The conjugate base is a good leaving group, which is what allows that electrophile to be what? What do we say? Nucleophiles do what to electrophiles? They attack. All right, so do it. Let's do our nucleophilic attack. We'll kick off that leaving group. All right, I'm going to try to be good in my mechanism with these double-sided arrows to show which steps are reversible and which steps are not reversible. And I honestly do not want you to get all too hung up on that. All right, I feel like we got enough on our plate without worrying about reversibility or irreversibility of certain steps. Let's just focus on the mechanism itself. So I'm going to be good. I'm going to be good in steps that are reversible versus irreversible, and I do not care if you commit it to memory or not. All right, we got enough to worry about at this point. We'll kick that can down the road. Okay, so then take a second and draw me my intermediate here. All right, what am I going to get after this step in my reaction occurs? Okay, now importantly, we kick off that water as a leaving group. But what is my organic intermediate here? We got a special name for these. This is a bond breaking / formation arrow. So I'm going to make a new carbon-hydrogen bond. All right. But what else am I going to form on this intermediate here? A carbocation. Awesome. So one of these carbons is going to get that carbon-hydrogen bond. The other one's going to be a carbocation. Which is going to be which here? Where am I going to form my carbocation? On the orange carbon or the green carbon? The orange. And why the orange? More substituted, meaning more stable of a carbocation. Right, so we'll get our new carbon-hydrogen bond over here, and we again have a mechanism with a carbocation intermediate. All right, so then again, I believe in you here. You're going to take a look at our reaction mixture, which contains water and a carbocation, and you're going to identify what the nucleophile is, what the electrophile is, and then do what nucleophiles do, attack that electrophile. All right, try to predict what the next step in our mechanism is going to be. All right, what's our nucleophile? The water. And what gives it away? Those lone pairs, right? Nucleophiles always have lone pairs. We also can just convince ourselves that this is definitely not a nucleophile because it's got a positive charge on it, right? Carbocations are great electrophiles. They can accept pairs of electrons because they themselves have an incomplete octet. All right, so this is the only sort of step here is including this bond formation arrow, which means that when I draw my next step, and I'm going to leave off this implied hydrogen over here. We all know it's there at this point, so I'm going to just leave it off. I have a new carbon-oxygen bond, but importantly, that oxygen still has these two hydrogens attached. So it's going to have a charge, absolutely. What's going to be my formal charge on this oxygen with its 3 bonds? Positive. Cool. So we're not quite there yet, all right? And to be clear, where we're going here, as we said, is an alcohol. Looking at our mechanism, we showed that this is going to be a Markovnikov reaction, right? We're going to put that OH group on that more substituted carbon. But we got one more step here to go. We got to get from this to this. What am I going to have to do? I'm going to have to break this oxygen-hydrogen bond, all right? But yes, we need some base to do it. We need something to accept that proton. And in our reaction mixture of a dilute acid, we have hydronium ions and water molecules. What do we think are going to play the role of a base, hydronium or water? Water, right? Hydronium is an acid. It's a very good acid, in fact. It's definitely not going to play the role of a base. Give that oxygen a +2 charge. That would be ridiculous. Instead, we'll have water playing the role of our base here. All right. You can also think about it as being a nucleophile, but specifically when our electrophile is a hydrogen atom, we can call it a base, or we do call it a base as well. All right, so our last step here, and this replenishes that supply of acid catalyst, right? I create a hydronium ion in the process. Cool. All right, so here is our reaction mechanism. As we said, we have this carbocation intermediate, which means that we have this Markovnikov reaction, right, where we're going to add that OH group to our more substituted carbon. There's regioselectivity, Markovnikov or anti-Markovnikov. We established it was Markovnikov. There's also stereoselectivity. With our carbocations, do we have to worry about stereoselectivity? Let's look back at our notes here. Our other carbocation intermediate reaction, our hydrohalogenation, did we say we have to worry about stereochemistry? No. Luckily, those carbocations are flat, so the nucleophile, that water molecule, will attack from both sides. We'll get a mixture of both possible isomers or a racemic mixture, so we don't have to worry about stereoselectivity. All right, great. Let's add this then to our list here. All right, we have this list that we've been making of our reactions. Now we're going to add our acid-catalyzed hydration. All right, so remember, we would either see one of two things in our list of reagents, either dilute sulfuric acid in water, or hydronium. Either one of these we need to know are doing the same thing. All right, and as we said, we're going to get an alcohol, and that alcohol is going to form on that more substituted carbon. All right, and we are keeping track of a few things on the side here to help us out with our cheat sheet. The first of which is whether or not we have to know a reaction mechanism. Do we have a mechanism for this one? Yes. And we can note that that has that carbocation intermediate again. All right, and maybe we should just note here as well, since we have another carbocation intermediate, what do we have to watch out for with our carbocation intermediates? Sometimes we get a product that we weren't really expecting, where something's added one carbon away from where our double bond is. And that's because what can occur with those carbocation intermediates? Those shifts, right? Either hydride or methyl shifts, but we're just going to note, just like with our other carbocation intermediate mechanism, we have to watch out for shifts. All right, we had regioselectivity. Are we going to have, is this one regioselective? Did it matter where I put that OH group? Yes, definitely. And since I put it on that more substituted carbon, what do we call it? A Markovnikov reaction. All right, but fortunately, We do not have any stereoselectivity. We'll always get a racemic mixture, so we don't have to worry about dashes and wedges with this particular reaction. Okay, so like we said, we have a hydration reaction. We're trying to add water. We can catalyze that with this just simple acid here. The only thing that's problematic about this particular way of hydrating an alkene is we have to watch out for these rearrangements that might happen, these hydride or methyl shifts. All right, so we have another method that we can use for hydration that will avoid that problem altogether, a method where we don't have to worry about any shifts. This is what's called a oxymercuration reaction. All right, this is where we take our alkene and we're going to hit it with something fancy here. All right, we're going to have a much more sophisticated set of reagents. We're going to use, let me make this straight, mercury acetate. So mercury, and then we abbreviate acetate as OAC. There's actually two of them. And water. And then in a second step, in order to get our alcohol product, we treat this with sodium borohydride. All right. This will also create a hydration product, an alcohol, and it will also be Markovnikov. All right, this is not a reaction where we're going to have a full mechanism for. I am just going to note what the intermediate is in this reaction. Okay. And that is another one of those cyclic intermediates. All right, and then importantly, the water that's in this mixture here is really important. This is going to be playing the role of the nucleophile, giving you your alcohol product. So this water molecule here, really the mercury acetate, it just turns your carbon-carbon double bond into a really good electrophile. Because what do we know about these three-membered rings? Are they nice and stable? No, they really want to open up because they are very unstable. So we turn it into a really good nucleophile, and our water molecule then attacks and opens that ring up. All right? So importantly, the water that's in our reaction mixture here is going to be the water that's playing a nucleophile and opening up this ring is going to be our OH group in our product. All right, it turns out that second step, the sodium borohydride, is there to kick off that mercury acetate at the end. Okay, again, we don't have a full mechanism for it. How did mercury attach itself in there? Don't worry about it, all right? The bottom line is, what I really want to take away here is that the water that's in this mixture here, that's in our reaction, our reagent list, is what ends up being our OH group in our product, all right? And that's important because although we can do an oxymercuration to create an alcohol like what we did here, a hydration reaction, we don't actually have to use water. We could use other weak nucleophiles. So for example, I could put ethanol in there. And let's try to figure out what our product would be. All right? So first of all, notice our neutral nucleophiles they always have to lose a hydrogen when they get attached, right? Because otherwise they would have a positive charge. So we're going to see these neutral nucleophiles will lose a hydrogen in their reactions. So I want you to apply that same thing here, noting that again, now this is going to be our nucleophile. Try to predict what our product is here if we did an oxymercuration in the presence of ethanol instead of water. Oops. All right, so now it's the oxygen in the alcohol doing the attacking. And the big difference is instead of having a hydrogen, it's got this alkyl chain on the other half. So instead of creating an alcohol, I've created what functional group? Ether, nice. All right, yeah. Cool. So we can use this method for creating alcohols, for doing hydration reactions. We could also include other nucleophiles as well. I could have an amine in there, all right? But yes, so this is our oxymercuration reaction. Let's go add it to our list here. All right, so here's our oxymercuration. We get our same product, that Markovnikov alcohol. Okay, in terms of our reaction mechanism, no, we don't have a reaction mechanism for this one. We are going to also just note here, we don't have a reaction mechanism, but as we said, there are no shifts to worry about. All right, regioselectivity, what do we got? Markovnikov again. And stereoselectivity, we didn't even look at our mechanism, but you're just going to trust me, there's none. All right, so to be clear, the only difference between these two here would be that carbocation intermediate where we can get these intramolecular rearrangements, these hydride or methyl shifts. Right? With that, our oxymercuration reaction, we don't have that problem. Practically speaking, then why would I ever do an acid catalyzed hydration? Because holy cow, is that way cheaper. All right, in terms of just practicality, we got a boatload of acid. You can get a gallon of sulfuric acid for pretty cheap. This mercuric acetate here, sodium borohydride, all of a sudden you're spending a little bit more, right? But the perks being you don't have to worry about those harsh conditions that lead to those shifts. You'll always just get that simple Markovnikov product. All right, so we got two ways to do it that are Markovnikov. What if I really want to create an anti-Markovnikov alcohol? Well, you are in luck. We have a method to do it. What's called a hydroboronation reaction. All right, before we even look at our list, our ugly list of reagents here, I'm telling you this is an anti-Markovnikov hydration reaction. So tell me what the product should be here. Hydration, we're going to get an alcohol product. But now which one of these carbons is it going to go on? The secondary or the primary? No, if it's anti-Markovnikov, it's going to go on the primary carbon. Okay, so how do we do it? We use what's called borane, BH3, in this THF solvent, tetrahydrofuran. And then in a second step, we add peroxide and sodium hydroxide. All right. Again, we're not going to learn a mechanism for this one. I am going to note the intermediate here. What happens is that borane forms this complex with your alkene. All right, and because it's sort of docking on one particular side of this alkene, you get that syn addition. So this is a stereospecific hydration method. All right, it's Markovnikov, it's regioselective, and it's stereoselective. It is a syn addition. All right, so let's add this to our list as well. All right, our borane and THF, followed by that peroxide and sodium hydroxide. All right, we again have, let's finish this off. We need to do our anti-Markovnikov product. Again, we didn't have a mechanism for this reaction. We can note there's definitely no shifts because it's anti-Markovnikov. It always forms on that less substituted carbon. All right, but so for our regioselectivity, we want to note that it is anti-Markovnikov. All right, and then as we said, our stereoselectivity is a syn addition. All right, so actually maybe let's put another example underneath this that illustrates that. Let's use a stereospecific alkene here, all right? And everybody's going to take a second and draw me our stereospecific product of our hydroboronation reaction to our methyl cyclohexene here. All right, so I got my 7 carbons here. Which one am I going to add my hydroxyl group to, orange or green? The green, anti-Markovnikov. And I'm going to be good, since I'm creating these 2 new stereo centers, I have to use dashes and wedges here. I'm going to put my hydroxyl group on this wedge here. So that means on my orange carbon, my hydrogen is going to have to be added to what? A dash or a wedge? If we're a syn addition, that means we're adding to the same side. So our hydrogen needs to go on a wedge as well, which means what do I got to do to that methyl group? I got to change it to a dash. Now that I've got 4 bonds on this carbon, I have to show my stereochemistry using those dashed and wedged bonds for my other bonds. I could have left off this hydrogen, to be clear. Right? I can leave that hydrogen implied, but I'm trying to illustrate that syn addition of our hydrogen and our hydroxyl. Is this a meso compound? So we're going to have to do both. Cool. All right, so we've got these 3 methods for hydrating alkenes, one being a simple acid catalyzed method. The only thing is you got to watch out for your carbocation intermediates because they can lead to those intramolecular shifts. We have an oxymercuration reaction, which is also Markovnikov, but we don't have any shifts to worry about. And then we have our hydroboronation reaction, which is anti-Markovnikov. We also got to watch out because this one has a stereoselectivity to it. It's a syn addition. So before we jump off real quick, these 2 are particularly intimidating lists of reagents here. All right. So to be clear, what do we have to know about these lists of reagents? All right. Remember, you don't have to have these things memorized. I'm not going to ask you to recite this list from memory here. You're going to have a reagent bank on your exam where we'll have all of our reagents listed together. All right. The important thing is that you can recognize what they do. So what you want to do is look for those key things that kind of jump out at you, that are unique to that particular list of reagents. An oxymercuration reaction has mercury in it, not an element we are used to seeing in organic chemistry. Very rarely will we see it, right? So we can key in on that one oddball element to help us figure out what's going on. We need to be able to sight recognize these things, right? Meaning look at it and know what it does. We don't have to have it memorized. So then everybody's like, oh my gosh, what is this thing in there? Don't worry about it. You know what your product is. It's an alcohol product. You have to remember that it's Markovnikov, right? But you don't have to worry about what every little thing is doing in here because we don't have a reaction mechanism. If you're genuinely curious, you absolutely can go look. It's in our textbook. It's a well-known sort of phenomenon what's going on here. But if you don't really care, then don't worry about it, all right? Same thing down here. If I look at my list of reagents, what element is popping out at me that I really just don't see very often? Right? We see hydrogens, oxygens, sodiums, I don't know, those are all over the place. THF, sure, this is a solvent, but we will see THF a few more times. Boron, though, is again not an element you see very often. In a hydroboronation reaction, it turns out that that boron is key. So again, just something that your mind can latch on to help you sight recognize these things. Rather than getting bogged down as to like what each thing is doing, again, if you're curious, you can go look up what the hydrogen peroxide is doing in this reaction, all right? But if you don't really care, then don't worry about it and just be able to sight recognize these things, right? Importantly, though, knowing that they are hydration reactions, knowing their regio and stereo selectivity, those are the important parts, okay? The last thing I'll say, studying-wise, is I know that I'm putting down the names of these reactions, and I feel like a lot of students are like, I'm not going to bother remembering that. That seems like extra information that I don't want to try to fit in my brain, all right? Importantly, though, the way that your brain works, the way that all brains works, is to categorize things, to put stuff into little boxes. And having a little title for that box is essential for me in my brain to keep track of all of this crap. All right? So I will tell you that for me, I have learned that I should know the names of these reactions. That is a sorting mechanism in my brain that helps me hold on to that information. So I feel like sometimes students are like, nope, too much, not going to bother. But trying to remember a random collection of facts is very difficult, right? Your brain sorts stuff out. And so those titles can help you sort things out. There's something to keep in mind when you're studying, not to completely ignore. All right, the last thing that we're going to do is compare and contrast these reactions here, these hydration reactions, using what's called a reaction wheel. So what I'm going to do is I'm going to put a substrate in the middle. And I'm going to put our various reagents in different directions pointing away from this substrate. All right, so our acid catalyzed, our oxymercuration, and our hydroboronation. And we're going to take this same substrate and we're going to draw the product of each of these reactions here. All right, so let's go through these here. We're going to start with the easiest one, which is our oxymercuration reaction. All right, that I say is the easiest because we don't have to worry about any stereoselectivity. We don't have to worry about any shifts. We just got to remember that it is what? Markovnikov or anti-Markovnikov for that oxymercuration. Markovnikov. So I'm going to look about my double bond here, and I'm going to note that I have a primary and a secondary carbon. Well, since this is Markovnikov, my hydroxyl group is going to form specifically on that secondary carbon. We're going to do our hydroboronation reaction because whereas oxymercuration is Markovnikov, hydroboronation is anti-Markovnikov. All right, so I'm going to put that on the less substituted carbon. Now, we also need to remember that it is a syn addition, but is this a reagent where I'm going to have to worry about my stereoselectivity, or rather, is this a substrate that I'm going to have to worry about my stereoselectivity? All right, let's just put it in and convince ourselves. Why don't I have to worry about stereoselectivity here? Is this a chiral carbon? No, is this a chiral carbon? No, so then I don't have to bother, all right? The tricky bit here is going to be our hydration reaction, and that's because we said because of that carbocation intermediate, I have to watch out for those hydride and methyl shifts. In this case, my secondary carbocation is going to form right next door to a tertiary carbon. And so what I'm going to see is a hydride shift leading to the alcohol forming on that more substituted tertiary carbon. So this substrate we chose in particular to stack these reactions next to one another so that we can really compare and contrast the differences between our hydration reactions. Right? Both oxymercuration and acid catalyzed are Markovnikov, but acid catalyzed you have to worry about hydride shifts that you don't have to worry about with oxymercuration reactions. All right. So we're talking about making alcohols using hydration reactions. We're also going to talk about making more alcohols, but we're going to talk about ways that we can make what are called diols. What the heck do we think a diol is? What do we think the di means? 2. So this will be a molecule that has 2 hydroxyl groups. Converting our alkene into a diol. All right, we got 2 ways to do it. I'm actually just going to go straight to our list to add this one here. All right, we can summarize it pretty easily. The name kind of gives it away here. This is a syn addition diol. All right. Since it is a syn addition, I'm going to go ahead and use a stereo-specific product or substrate here. Holy cow. All right. This uses osmium 8 oxide. Followed by sodium hydrosulfite and water. Again, if I'm going to kind of latch on to anything that jumps out at me, we do not see osmium very often at all. All right, so just something little that I can latch on to help me recognize this particular one. And if I'm going to form a diol. So we're going to add an hydroxyl to either side of our carbon-carbon double bond. If I'm going to put one of these hydroxyl groups on a wedge, what's my other one going to go on? Just straight up in the name, right? This syn addition diol. Also going to go on a wedge. All right, and remember our cis rings here are these plane of symmetry meso compounds, so I only have to include that one structure. We do not have a reaction mechanism. What about regioselectivity? Does it matter which side I put my hydroxyl group on? No, why don't we have regioselectivity? because they're both the same, right? In our addition reactions, halogenation, both bonds are the same, no regioselectivity. Hydrogenation, both bonds are the same, no regioselectivity. Same deal here. Both bonds are the same, no regioselectivity. All right, but then our stereoselectivity, as we noted, is a syn addition. All right. I know, try to contain yourself. This is our last reaction of this chapter, I know, which is very sad because everybody's having a lot of fun here. But we got one more to go. This is another diol, but this is now going to be the anti-addition. Diol formation reaction. All right, and we'll talk about reagents here in a second. All right, but what we're going to do in our anti-addition diol formation is we're going to take our alkene and we're going to first convert it into this thing here, a three-membered ring with an oxygen, what's called an epoxide. So we're going to convert our alkene into an epoxide. We see our epoxide's got this three-membered ring here. Are three-membered rings nice and stable? No. So it turns out that all you got to do is treat this three-membered ring with a dilute acid, and it will pop open, giving us a diol. All right, so how do we do this here? How do we, as I said, we just treat our epoxide with dilute acid to get our product. How do we get our alkene into an epoxide? There's actually two ways that we're going to learn how to do it. One is using what's called a peroxy acid, CO3H. CO2H is a carboxylic acid. So this is, again, what we call a peroxy acid. All right, so everybody just take a second and convince yourselves that this is a carboxylic acid group that we're looking at here. Cool? Right, we all recognize a carboxylic acid group? All right, if I'm going to make a peroxy acid group, it's not CO2H, but CO3H. I'm going to need another oxygen in there. So we have this very weird, what we don't see very often, oxygen-oxygen single bond here. All right, and we'll see peroxy acids pop up a few times throughout the course. They're always doing the same thing, which is kind of weird. They're sticking that oxygen in between an existing bond here. So in this case, my carbon-carbon bond, that oxygen gets inserted between that carbon-carbon bond, forming our epoxide, our little triangle here. We don't have a mechanism for it. We just need to be able to recognize that. The other way, though, we're going to spend some time talking about, because it's our first sort of multi-step synthesis here. We're going to do one of the reactions we've already learned about in this unit here, our halohydrin formation reaction. using bromine and water to create a halohydrin. And then if you treat that halohydrin with hydroxide, really we should be good and include our counter ion. They like to use potassium hydroxide for this. I don't want to get too much into it. Sodium hydroxide, whatever. The hydroxide's the important part. Okay? So we're going to take a look at our mechanism here. For the sake of time, I'm going to skip over because we've already done it. It's already in your notes. Going from an alkene to a halohydrin. So I'm going to focus on how we go from that halohydrin to our epoxide. All right, a halohydrin, remember, has a OH group and a halogen, all in the same molecule, located next door to one another. Okay, and be good and put in my lone pairs. All right, so we're going to now add in that hydroxide ion. What do we think is our nucleophile here? Our halohydrin or our hydroxide? To be clear, both of them could be a nucleophile, but which one do we think is going to be a nucleophile in this particular example? Which one's the better nucleophile? The hydroxide with its negative charge, all right? So, and I'm going to even tell you that it's not just a nucleophile, but it's going to be playing the role of a base, meaning it's going to be accepting a proton from this molecule here. So let's look carefully. Is it going to be easier to deprotonate a carbon or an oxygen? Which ones are the stronger acids, carbons or oxygens? Oxygens, right? You're going to have a hell of a time. You are just like almost never in your life going to see a carbon getting a hydrogen pulled off of it. It's very, very hard to do. They hold on to their hydrogens very tightly. So indeed, we're going to be deprotonating our oxygen here, creating our intermediate. All right, this comes off as water. Won't be involved in our reaction anymore. All right, so, and again, we're going to see if we can't figure out where we're going here. I should be good. This is a reversible step. All right, so always helpful to keep in mind what our product is, this epoxide. I want you all to try to figure out what's going on in this next step. And let me just give you a little hint here. All right, within this molecule, we have both a nucleophilic site and an electrophilic site and a leaving group, all in the same molecule. All right, so we're going to have this intramolecular reaction here to create our epoxide product. I want you to try to identify what the nucleophilic site is, what the electrophilic site is, and what your leaving group is, and then put in your electron pushing arrows, all right, given what we've discussed about our mechanisms up until this point. See if you can't finish this mechanism off on your own. All right, what's your nucleophilic site? What's your electrophilic site? What's your leaving group? All right, there's just two arrows that you'll be putting in, one bond formation arrow and one bond breaking arrow. All right, another good strategy for mechanisms. What bonds do I need to form over here? What bonds do I need to break over here? All right, so within this molecule, what's my nucleophilic site? What's glowing red hot with electron density here? The oxygen with its negative charge. All right. And what's my leaving group going to be? That bromine. So then where's my electrophile? My carbon, right? Remember, this polar bond here means that carbon's got a lack of electron density, bromine's got a lot. So that's a good electrophile. And so what's going to happen? Oxygen's going to attack that carbon and kick off that leaving group there. All right, so to be clear, oxygen is our nucleophile, carbon is our electrophile, and bromine is our leaving group, creating our epoxide. Epoxides are pretty cool. We'll revisit them in the next semester and talk about even more reactions of them. All right. So now we're going to do one more here, going from epoxide to diol. All right, so the very first step here I'm going to give you because it's not super obvious. Although we will see it a lot. It's a strategy that we'll see a ton when we're talking about these oxygen-containing functional groups in acidic conditions. But the very first step in our mechanism here is going to be to protonate that epoxide oxygen. All right, and the reason that we're going to see that is because it just makes that oxygen an even better leaving group. It makes it much easier to break that bond. All right, our next step here is going to involve that water molecule that was formed and our epoxide. Does our epoxide have any polar bonds in there? Is oxygen and carbon the same electronegativity? No, oxygen's very electronegative. So there's my partial negative charge. You could pick either carbon to have that partial positive charge. All right, and then water, we see play the role of what? Our nucleophile or our electrophiles? Nucleophile. It's a weak nucleophile, but it's a nucleophile. All right, so given this here, we're going to see our water attack that partial positive carbon, and our epoxide ring is going to pop open here. Again, these ring opening reactions that we've seen a bunch when we've had these cyclic intermediates. All right, I guess I'll stick to my Lewis structure here. So I'm almost there. I'm almost at my diol product. Bless you. All right. What do I need to do to convert this into an alcohol group? I need to break that oxygen-hydrogen bond. And so I need something to accept that hydrogen. In our acidic conditions, what do we use as a base? Do we have hydroxides floating around? No, we don't have any strong bases like that. What did we use when we did our pause for dramatic effect. We had this same situation in our acid catalyzed hydration where we needed to remove a hydrogen to form a hydroxyl group. And so what did we use as our base? Water. Right? Under those acidic conditions, we have a bunch of hydronium and water floating around. Hydronium is definitely not going to be a base. So we need another water molecule in our solution to do it. All right, so that last step is going to form hydronium, a new oxygen-hydrogen bond, and we get that lone pair of electrons on that oxygen to create our diol here. All right, now, given this mechanism here, oh, I guess I kind of gave it away in the title here, but let's just see if we can convince ourselves. Since this is this ring structure here, my water cannot attack from this side. It has to attack from the back side. And what type of addition do we have with these cyclic intermediates? An anti-addition, all right? Which again, I did kind of give away the punchline up here, but nonetheless, all right? So we have one more to add to our list here. This is our anti-addition diol formation. All right, and just for the sake of kind of clarity, I'm going to break this up into two steps here. We can either use that fancy peroxy acid or that halohydrin followed by base. Okay, this forms an epoxide. If I'm going to make an epoxide with my ring here, can I have one bond pointing up and the other one pointing down, being bonded to that same oxygen atom? No, they got to be pointed in the same direction. So if I'm being good here with my stereochemistry, I'm going to show my epoxide. I'm just going to pick one. All right, we're going to get lazy and save space and just say plus En, meaning plus it's an enantiomer. All right, and in that second step, we're going to follow it up with that hydronium ion, and we're going to get our anti-diol. Meaning one of those oxygens is on a wedge, and one of them is on a dash. Okay, and so then let's do the last little bits here that we need. Reaction mechanism. Yes. Right, we do have a reaction mechanism, and this is our first example of a multi-step synthesis mechanism here. I guess I should say yes for specifically the Br2, H2O, KOH, and dilute acid method. We don't know how this peroxy acid works. But for the other method, we actually know all 3 steps in that mechanism. What about regioselectivity? Why don't we have it? Same bonds. All right, but our stereoselectivity is that anti-addition. All right, cool. One more thing to note about stereoselectivity is that it is obviously the worst part of all of these reactions, right? It's definitely the hardest thing to get correct every time, the stereoselectivity. You're definitely going to have homework assignments to practice it and all of that sort of thing, but it is worst case scenario. Are all of your questions on the exam worst case scenario questions? No. Can you expect to see a few worst case scenario questions on the exam? Yes, okay? And that's kind of how you want to treat this. You're going to have certain homework assignments where I'm like, look, don't worry about stereochemistry. Make sure you've got the reaction down. Make sure you've got the regioselectivity. That's kind of the easy part down, or definitely the most important part. The stereoselectivity is then that extra added little bit of difficulty. You can definitely expect to see some, but again, you don't have to get so stressed out about it as if that's the only thing that I'm going to be testing on, right? That is the kind of last aspect of these reactions that you should be focusing on. Making sure you know what your product is, right? What functional group did we just form? In all these cases today, we made these alcohols, right? It's definitely something that should be first and foremost in your brain. And where does that alcohol group go? Those are by far the most important things about the reaction. The stereoselectivity is important, but again, that's what I would focus on last in my study. Okay? Cool.